has a great heat pump application to global warming, because for every 1 watt of power that you pump in, you're actually extracting 1.3 watts of environmental heat. So there you go. So say we wanted to just build one. So a typical visible light LED, and if we wanted to construct one, say with a certain size emitting surface and wattage and a wavelength in the visible spectrum, so it's greater than, say, a certain wavelength, and then the extra energy has to come from somewhere, so it's just connected to a heat sink at some temperature. And so what happens is that this radiative heat, it comes from the lattice. In my longer lecture, you can read if you're, or watch if you're interested, is that what it turns out to be, you can work through, is that it's like a refrigerator, is that it cools down the environment. You do a little bit of work by the electrical power input, and it takes energy from the cooler environment, and then it outputs radiation at a temperature T1 in terms of the electromagnetic spectrum. And the curve is shaped like this. And as you can see, if you can see this graph, the efficiency does decrease by temperature, but we have to find the best operating temperature of the LED is at. And that is just simply by knowing that, well, if we want to have a good wattage of the LED, in this case, if we had a surface area, emitting surface of a millimeter squared, and an output power of a microwatt, then that means it's a radiance. Its intensity is a watt per meter squared. But using Stefan Boltzmann's formula, integrating, say, over the visible range, and this is just the Boltzmann's formula, it gives you this. You just have to solve for the temperature, and knowing that the wavelength has to be in the visible spectrum, you find that the temperature would have to be at least this large number. Whether that's physically feasible or not is not true, but maximum efficiency 36% for this higher wattage visible LED. But in short, we can do much better than this if we aren't so stringent on what we want. In for a near infrared LED with an power of picowatts, they got an output power of 69 picowatts, which meant they got an efficiency of more than 230%. For every watt you have, you can extract 2.3 watts of heat from your environment. So that's one application. So thank you very much for that.